Engineering 305, problem 826. This is, I'm not even going to tell you what attempt it is. But we got a cantilever beam shown, which has a moment of 2I at the beginning and 1I at the end. And so I've been writing that on here. 2I, and this is I. And then they want us to find the deflection at B and the deflection at C. So the first thing I'm going to do is put coordinate system on here, right? This is my y direction, there's my x direction. And I'm going to go through and find my reaction forces. So there is, of course, going to be a reaction force here. That's the reaction at A. And there's going to be a reaction moment at A as well. Sorry, that was really sloppy. Moment at A. Okay? And we go through and we solve it. So I've got the sum of the forces in the y direction are equal to 0. I'm working across this over here. And so I get the reaction force acts up. I've got minus P twice. I've got that P force acting down. And so the reaction force is equal to 2P acting up. And then I've got to go through my moments. I'm going to do some of the moments about 0 or about the origin. And so the moment acts in a positive way to get it to rotate. And then both of the point loads, P, act in a negative direction or cause it negative rotation. So the first one gives it a rotation, or it's only acting a distance L away. So it's minus P times L is the moment. The second one, however, is 2L away. So my moment, if I go through and solve that, my moment is actually 3 times the load times L, 3PL. So the next step would be to go in and draw in that arbitrary cross-section and put on my VR and put on my MR and then solve for what that is. Well, I didn't even bother solving the shear equation. I just jumped right to the moment equation. And so that looks like this. The sum of the moments about that cut are equal to 0, are equal to MA. That's that moment at the beginning. That's the reaction moment. And plus MR, those are both causing it to rotate from X to Y. And then minus RA times X. That's actually going the other way. Now, I substituted in this line, I substituted in those values because I knew what they are. MA was equal to 3PL, MR, and then the RA was equal to minus or equal to 2P times X. And so then I went through, substituted, simplified, and there's my equation for MR. MR is equal to 2PX minus 3PL. Okay? I integrated that twice. I got EI theta and I got EI delta. All right. When I integrate, oh my goodness. When I integrated 2px, that gave me 2px squared over 2. So we canceled that. Minus 3pl times x plus a constant. Got to include the constant. And then I got the next expression. Now I need to apply boundary conditions. All right. So let's apply some boundary conditions. What do we know? Beautiful thing about the cantilever beam. Beautiful thing about the cantilever beam is delta, not delta equals 0, but it is. It's delta at 0 is equal to 0. Excuse me. So, if I look at this equation, I've got, if I say EI delta, put that, then I can just write this equation. Px cubed over 3 minus 3 halves PLx squared plus C1x plus C2. Now, let's eliminate all the terms that have an x equal to 0 because they go away. That one's gone, that one's gone. Oh, look, the only thing left is C2 equal to 0. Got rid of everything. Oh, isn't that a beautiful thing? Same thing is going to happen with the EI delta equation. Because I know that delta theta, the angle at 0 is equal to 0. Well, that's going to eliminate the first two terms that have an x, and the only thing they'll leave me with is C1, which is therefore equal to 0. So we have the equations for x, I got to write it this way, for x between 0 and L, EI theta of x is equal to px squared minus 3plx. Yep, there you go. I like that. And EI delta as a function of x is equal to px cubed over 3 minus 3 halves plx squared. All right. Cool. Now, we got a couple things we could do here. I'm going to opt for this one. And that is, we're going to write... Oh. Sorry. Let's jump back one small step here. One small step. Because the first question is, what's the deflection at section B? And I can calculate that. At section B, at B, x is equal to L. So delta of L is equal to, or I'm going to say EI delta of L is equal to PL cubed over 3 minus 3 halves PL times L squared. That's the x squared. So that's equal to, look, I've got a PL, or I've got a 1/3 minus 3 halves PL cubed. Sorry. PL cubed. Oh, let's see. 1/3, that's equal to 2/6 minus 6. Sorry, minus 9/6. 2/6 minus 9/6 PL cubed. So that's equals negative 7/6 PL cubed is EI delta. And maybe the way that you want to express that would be delta is equal to minus 7/6 PL cubed over EI. Maybe, maybe not. I don't know. There's a reason for leaving the EI on the other side, but I'm not going to get there right now. So that is the deflection at B, or at delta equal to L. There's the answer for the first half. Let's write. Now what we need to do is we need to go back to the beginning in a sense, and we need to say, look, here's my beam. And now I need to take and write my equations at any arbitrary section there, L. Well, I'm going to jump right back into my moments. Some of the moments about my cut are equal to, do you remember? I had the moment at A. I had the reaction force at A. Let's go look both of those up, just so that I put them in right away, because I've already forgotten them. The moment is A at 3PL and then 2P. Right. So this is equal to 3PL, and this is equal to 2P. So the sum of my moments at around C, around the cut, equal to 0, are equal to my moments at A plus, oh, sorry, it's going to be a minus 2P times X. I've got my, I got to put in that reaction moment, which is going to be is also going to be a plus mr, correct? And what I'm missing is what I failed to draw in there is I have that p, and that is that's also going to give me a negative moment. So that's a minus p, and now the distance is not x. The distance is x minus L. X minus L, because this was L away. So the distance from this distance here is x minus L. That's x all the way out to there. There you go. Got it? Got it. Got it. There's my moment equation. Oh, what I didn't substitute in. Sorry, what I want to do is write that as 3PL, because this I've already converted over into P's. Okay? Integrate that twice. EI theta. Oh, sorry. You know what? Before I do that, I want to rewrite this. MR is equal to minus 3PL plus 2PX plus P times x minus L. Okay? Just write that out. Makes it a little. Just I got that. Now I can write EI theta is equal to minus 3PLX plus PX squared. The 2's went away. Remember that? Because it's going to be the same term that we had before. And then plus a P X minus L quantity squared over 2. Yeah. Plus a constant. Plus constant. I just put constant 1 because I'm thinking that's the first time I've integrated. Earlier in the problem, I already had a C1, so maybe I call it C2. No, I had a C2 also. I'll call it C3, just for clarity. And then I can integrate one more time. EI delta is equal to minus 3PLX squared over 2 plus PX cubed over 3 plus P over 6 x minus L cubed plus C3 x plus C4. You good? Except my face is in the way, the C4. Yeah, don't get your face by the C4. That's bad. That's how the 4th of July accidents happen all the time. All right. Let's keep chugging away. So where are we? What do we need to do? What's our next step? Boundary conditions. What boundary conditions do we have for this portion of the beam? That beam, this equation, these equations are only good for x between L and 2L. So what boundary conditions do I have? Do you know of any? Well, I got one. And that is delta at L is equal to minus 7/6 PL cubed over EI. What? Where did I come up with that? Well, that is what we had up here. That's what we had up there. We solved this equation. This equation, if we look at our system, let's go down where I can scribble a little bit. We wrote an equation for this portion of the beam from 0 to L. And then we solved it for the deflection at B. Well, the deflection at B, if I go from this side or if I go from this side, the deflection has to be the same. So There's my deflection. Now I want you to be careful about one thing. And that is what I didn't do here is when I put in I, that I is equal to 2I. So this should probably have a 2 there. Because now when I get down to this section, I change I. And I don't like these problems because we get errors just because I is not equal to I. And we're actually using the same variable 3 different places. We're using it in the equations EI delta equals something, and then we use it for the section modulus for the first section, and we use it for the section modulus for the second section. That gets confusing. Now, that gives us, here's one boundary condition, and honestly, if I plug, well, no, I can't just plug that in. I can't. That gets complicated, right? That gets complicated. But I can do that, and now I need one other boundary condition, and that would be theta at L, which is equal to, and I can go back here and find out, because I have this equation here. So if I plug in L, then I'm going to get PL squared, and that's equal to, at L, sorry, PL squared minus 3PL squared. So theta is equal to EI theta is equal to minus 2PL cubed. No, PL squared. Minus 2PL squared. Right? EI theta at L is equal to PL squared minus 3PL squared, which is equal to minus 2PL squared. So there's my other boundary condition, and that's EI, E2I. Again, how you manage that, and I'll let you, I've already forgotten what I wrote. Minus 2PL squared. Minus 2PL squared. All right, so there's your two boundary conditions. There. These two. Those two. All right, so now you can establish what the equation is for the second half of the beam using those boundary conditions to figure out what your constants C3 and C4 are. Okay? I'm not going to sort that out 9:20 at night. I'm just going to post this so that you can take a look at it. I hope you're doing well. Don't worry, there's more coming. I got a full plate for tomorrow of all the things I want to accomplish. I hope you're doing well. See you.